The idea for today's lesson comes from a subscriber request. We start a programming journey by learning about a programming language, so it's only natural to want to create our own at some point in your career. I've toyed with a number of compilers over the years, so in this lesson I will break down the fundamentals that you need to know in order to build your own programming language. We will use the TypeScript compiler as inspiration and then simplify it way down only to the bare necessities, so let's go. As you would expect, the programming language that we are going to create is going to be pretty basic. Fundamentally, you will have the ability to invoke a function, and the only function that you have available to you is going to be the log function. And the only data type that's going to be available is going to be numerics, which is numbers, and even then just basic integers. And then in terms of mathematical operation, you will have plus and minus available to you. And as mentioned, we're going to take inspiration from the TypeScript compiler. And this particular statement that we have over here is actually perfectly valid TypeScript code as well. And we can actually see how this particular code is represented within TypeScript's brain by using the TypeScript AST viewer. Of course, if this is the first time that you are looking at something like this, you might feel a bit overwhelmed, but don't worry, I'm going to break it down into the two key things that are happening within the AST viewer. The first thing that is happening is tokenization. Tokenization is something that is going to take a stream of code and convert it into well-defined token objects. This is a pretty easy step, but it will greatly simplify how we interact with our source code within the compiler. And we can actually see these tokens within the AST viewer. For example, identifier is a token, an open paren is a token, a numeric literal is a token, and in fact, all of the tokens are still represented within the abstract syntax tree. This of course brings us to the second concept, which is parsing, which is going to take our tokens and convert them into this tree-like structure called the abstract syntax tree. The AST is just a reorganization of the tokens into more logical groups. For example, we can think of the whole of this code as a call expression. Similarly, the argument to the call expression can be categorized into something called a binary expression. And the right side of this particular binary expression is just another binary expression between two numeric literals. And this is exactly what we see within the TypeScript AST viewer as well. We have the call expression as well as other familiar nodes, for example, the binary expression. Now, of course, there's a lot more that's going on within the TypeScript compiler as well, but I don't want you to get bothered about that. We're not going to be building the whole of TypeScript. However, I wanted you to know that we're going to be grounded within some actual production compiler code. And this will bring us to the next piece of puzzle that we will implement, which is the emitter. We will start off with some code input, convert it into tokens, convert these tokens into an abstract syntax tree, and then finally we will demo how easy it is to work with this abstract syntax tree to generate some executable code, for example, valid JavaScript. To kick us off, we will take inspiration from the TypeScript compiler itself by first creating a file that will store all of our types. Now, the first thing that we are focusing on is creating the tokenizer, and of course, the key types over here are the different kinds of tokens that we can possibly have. Our programming language is pretty simple, so we will only need a few of these. The next step is to create a general type for any given token, and that's simply going to be a union of all of the tokens that are present within our programming language. And that's it for the types that we will need for our tokenizer, so let's jump into our tokenizer file and create the function that will do the tokenization for us. The tokenizer is going to take an input code string and return a set of tokens. And we are going to do it in the simplest way possible by creating a cursor, which is going to be our index into the input string that we have yet to look at. In each iteration of the loop, we will grab the current character using the cursor pause, and then use this character to determine what kind of token it should be. First off, if it's white space, then we're simply going to ignore it and move on because we don't care about white space within our programming language. Next up, if it's an opening parenthesis, then it's going to be pretty easy. We create a token for open parens and then increment the cursor to go on to the next character. And we have a number of other tokens within our source code as well that are pretty similar, and we can handle them the same way, which is the close parens, as well as the plus token, as well as the minus token. Now the next token that we're going to handle is not going to be as simple as these ones, and that is the numeric literal. First off, we have a very simple regex to isolate any numeric digits. This is what we will use to jump into a numeric state machine if the particular character matches. The state machine is going to loop through the characters, and as long as they continue to match a numeric literal, they're going to be stored within this value string. And once it stops matching, that is when we will create the numeric literal token, and then we can continue the loop with the character that failed to match, and therefore don't need cursor pause ++ in this particular case. Our next token is going to be very similar, and instead of numbers, we're going to be working with letters. Our identifiers are only going to be letters in the range A to Z, no underscores, no numbers, just to keep things super simple. This makes the code for the identifiers very similar to the numeric literal one, where we simply check if it is an alphabet, and if so, it continues to get added to the value, and once it stops being an alphabet, that's when we know we have our identifier, and then create the identifier token, and then continue with the character that failed to match. Next, we will take an inspiration from a recently released programming language called Bylang, which within its tokenizer will throw an error message "Kya kar raha hai tu" when it experiences an unexpected token, and we will do the same within our tokenizer by throwing a syntax error with the same error message for this particular character. And that's it. Congratulations, you've created the tokenizer for TS And in fact, the simple code to token stream that we have seen before is from the simple tests that I have for this tokenizer. Now the next step is to create the parser that will take these tokens and convert them into the abstract syntax tree. But before we do that, here's another piece of inspiration from the TypeScript compiler, where we group different sets of tokens into more meaningful names, for example the plus and the minus token into the additive operator. Jumping into our types, we start creating the types that we will need for our parser. First off, we have this additive operator, followed by the list of nodes that will exist within our abstract syntax tree. The numeric literal node is pretty easy. However, I want you to know something about the call expression node in that it contains a member called argument, which can be any node that we might have within the abstract syntax tree. The same is true for the binary expression node. It has a left member, which can be any node, as well as a right member, which can be any node. And the operator for the binary expression can be a plus token or a minus token, which we have grouped into the additive operator. And just like we have with the tokenizer, a general token type, we have this general node type, which can be any of the nodes that exist within our AST. Now the output from our parser can be an array of nodes, but it's easier if we consolidate it into this concept called a program, which will contain the body, which contains an array of root level nodes. Now our parser function is going to be this function that is going to take an array of tokens and return a program. At its core, it's going to be a simple while loop into the tokens, and for each iteration of the while loop, we will use this utility function called parse, which is going to parse any number of tokens that it needs in order to create a meaningful AST node. Now because abstract syntax tree nodes are recursive, for example a binary expression can contain another binary expression, it makes sense to do parsing as a recursive function. Whenever you need to parse anything, just call parse and you're good to go. At its core, the parse function is going to look at a particular token, determine the kind of token that it is, and make a decision on what kind of parsing that it needs to do based on that particular token type. For example, if the token is a numeric literal, it's going to call this function called parse numeric literal, which will increment the current counter to eat up this particular token and then return an AST node of type numeric literal. A more interesting parsing scenario is going to occur when we're going to encounter the token identifier. Within our programming language, the only case an identifier is supported is in a call expression, and therefore we can offload the hard work to this function called parse call expression. The parsing for the call expression is going to be a bit more involved, and hopefully we get to see the value of using a recursive parsing function instead of a simple loop-based state machine that we used for the tokenizer. The first token that we are going to eat within parse call expression is going to be the identifier, which we are simply going to store into an identifier variable and then move on to the next token by incrementing the current counter. Now the next token that we expect within our call expression is to be an open parens, and just in case it is not an open parent, we're going to throw a syntax error and simply exit the compiler. Now the next thing within our call expression is going to be the argument to the call, and we're assuming that we're going to allow all forms of code within the argument, and for that we are using the general purpose parse function. If we wanted to restrict the argument, for example only allow a numeric argument, we would call the specific function, for example parse numeric literal. Finally, we expect the next token to be the closed parent token, and if everything goes according to plan, congratulations, we have our call expression node. Another feature that is common within parsers is this concept of lookahead. As an example, here is some sample code from the TypeScript compiler. In addition to looking at the current node, you need to look at a few future nodes in order to determine which kind of parsing you need to do. For example, when we look at a numeric literal within our code, it might actually be a numeric literal node, or it might just be a binary expression. So we look at the next node that is after the numeric literal to make sure if it is a plus or a minus token, then we parse it as a binary expression. Otherwise, we parse it as we did before as a numeric literal. And now that we've seen the code for parse call expression, the code for parse binary expression is going to be pretty easy. First up, we grab the current token that we are on as a numeric literal. Then we store the next token as an operator because we've already verified that it is either a plus or a minus and it's passed into us, and we eat it up with current plus plus. Next we eat whatever is on our right hand side by simply invoking parse recursively, and congratulations, if everything goes to plan, we have our binary expression. And just like we did within our tokenizer, if we encounter something that we don't know how to parse, we will throw a syntax error with an unknown token. And that's the entirety of the parser for this super simple language ts-. And in fact, the example for the AST that we saw before is from the test for this particular parser. In compiler theory, a compiler is broken into two stages. There is the front end of the compiler, which takes input source code and puts it into the brain of the compiler, and then there is the compiler backend, which takes it from the brain of the compiler into some form of output. For example, in the case of TypeScript, it produces output JavaScript. We will take inspiration from the TypeScript compiler and convert our code into JavaScript, and we will create this file called emitter, which is what it is called within the TypeScript compiler as well. Our emitter is going to be a simple function that is going to take a program, which is our AST, and return the generated JavaScript output. Now, due to the recursive nature of the AST, just like it's easier to create the AST with recursive functions, it's easier to navigate ASTs with recursive functions, and that's exactly what we will do within our emitter. At its core is going to be this emit function that is going to be designed to emit any node. Now, our AST is pretty simple because of the limited feature set of the language that we have designed, so our emit function is going to be equally pretty simple. It's a simple switch statement over node.type and offloads all of the hard work to the individual emit functions for that particular node. First up, for a numeric literal, all that we need to emit in the generated JavaScript is node.value. For emitting a binary expression, we use our utility emit for the left as well as the right nodes, and for the middle operator, we use a ternary to map it to a plus or a minus. For our call expression, we are a bit more restrictive. The only call that we allow is to the log function, so we make sure that the identifier is going to be log. And in that particular case, we map it to the JavaScript console.log statement, otherwise we throw a syntax error. And that's the entirety of the emitter. Because our input source language is very similar to our output target JavaScript language, our emitter is quite simple. With all of these components out of our way, let's create a utility function for our compiler. It will take an input source code, pass it through the tokenizer to get the tokens, then pass those tokens through the parser to get the AST, and then hand over that AST to the emitter to get the output JavaScript, which we will then return from our compiler function. Now, the TypeScript compiler doesn't come with an interpreter because its output JavaScript is executable in a large number of environments. However, there is this thing called tsnode, which can be used to run your TypeScript code without having to compile it first. So we will create something like that as well in our interpreter. And fortunately, because our compiler is running in JavaScript, we can run the generated JavaScript with a simple call to eval. To allow people to invoke our compiler, we create a simple file, which will have an async main function, which we will invoke immediately. And within our main function, we grab the command line arguments, excluding the node executable as well as the name of the script. If the user provides a ---- run flag, we note that down and then exclude that further from the arguments. And now if we run out of arguments, then we throw an error that please provide us an input source file. Otherwise, we read this particular file and note down its contents into this input string. With this admin style code out of the way, let's jump into the meat of the main file, which is going to be the code that is either going to compile it to an output destination file, or it will interpret it in a live fashion. We use the compiler to convert the input source code into the output JavaScript. If the run flag was provided, we simply invoke the interpreter. Otherwise, we write the generated output into a .js file right next to the input source file. And now for the moment of truth, we create this file basic.tsmm, create some source code in our input source language, run this through our compiler by invoking our index file, passing in the name of this basic.tsmm file. And fortunately, everything works as expected and we get the output that we wanted. Now, one more thing that we can try is pass in the ---- run flag to just evaluate the output JavaScript within our console. And of course, the output is what you would expect. 1 + 3 - 4 is equal to 0. Now, in addition to a single log statement, we can actually add as many log statements as we wanted. For example, here's some maths that I don't want to do in my head. So I will run this, and there's the answer. And that's it for this lesson. Hopefully you appreciate the effort that went into making this compiler as well as presenting it in an accessible fashion. If you did, then smash that like and subscribe and turn your thoughts into comments. Personally, I don't have the need to create my own compiler because TypeScript pretty much does everything that I want and it's pretty darn advanced. For example, here's a lesson where we look at one of its advanced features called map types. Thanks for joining me, and I will see you in the next one.